joint work with people from EPFL, UCL, and Trinity College. First, we can look into some motivation. Our motivation for this project came from talking with actually potential blockchain clients and seeing that they've heard a lot about the promise of blockchain, and we wanted to see what is out there. So if we look into what people think a blockchain can do, they think that a blockchain could actually very easily be used to transform electronic health record keeping, to put our data on chain to protect them. We can, for example, use a blockchain for e-voting, or even use it in order to calculate premiums and insurance companies. However, all of these applications require data access on sensitive data that should remain confidential. And if we look into existing blockchains, then we actually see that they do not respect the CIA triad that data management systems should respect. Specifically, although blockchains provide very strong integrity compared to some databases through the use of cryptography, and very strong availability because of the very wide, large-scale application, they do not enable confidentiality. And they do not enable confidentiality because data has to either be unavailable because it just encrypted on-chain and never reveal them, or it has to go on-chain publicly, at which point it's of course not confidential anymore. More specifically, if we look into some applications that we want to deploy with blockchains, we see two very clear categories. On the one hand, we would like to use blockchains to do decentralized auditable data management. In this setting, we have some mutually distrustful parties, whether we have some business ecosystem where people trade with each other but still have their business secrets, or state actors that, for example, try to catch terrorists, but they can just reveal all their state secrets. In this case, we want some way to access data, but to be auditable and authorized. On the other side, we have all those finance and gaming applications that are susceptible to front running. These are applications like decentralized lotteries, poker games, or trading. And in these applications, we want to have some clear barrier point before which users make their bids, play their game, and no one can see the moves of the other players. And after that, everyone atomically accesses the data so that there is no arbitrage opportunity. And this is, again, not possible with existing blockchains. Let's look into a very Strawman specific application. Here, Wanda wants to send some private data to Ron, but because Wanda and Ron are concurrently available, we're going to use a blockchain to preserve the integrity and the availability of data and make this exchange asynchronous. So Wanda encrypts the data for Ron, sends it to the chain logs it, and then Ron can ask some node from the blockchain to give him the encrypted secret, which he decrypts locally. So we achieved our goal here because the data was available. Even if Wanda went away, Ron could access it, and the data was not altered by the blockchain because of all the cryptographic guarantees. However, this way, we still have a lot of shortcomings. Firstly, Wanda has no control over her data. The moment she encrypts for Ron, it can stay there for decades, and she can never actually revoke access. Secondly, Wanda does not know if Ron accesses the data. So if Wanda had some agreement of Ron paying her to access the data, she cannot actually claim payment. Or if the data gets leaked, she cannot actually blame Ron for this leak. Thirdly, if Wanda wants to share the data with more than one user, she has to create multiple transactions, which will quickly blow the chain. And finally, Ron is going to lose access of the data if he loses his public key. In order to resolve all those problems, we designed CALYPSO. CALYPSO has 6 specific properties that we want from a data management system that is decentralized. First, we want it to be auditable. Any access for the data has to be verifiable and tamper resistant. Secondly, we want confidentiality, of course. Thirdly, we want decentralization. We can't have a trusted party. We also want fair access for all those arbitrage opportunities that we want to stop. Fifth, we actually also want receiver anonymity. We want to be able to not publicly announce that Wanda and Ron are transacting, but at the same time preserve auditability. So Wanda still is able to blame Ron, although no one else knows that Wanda and Ron did transact. And finally, we want dynamic and sovereign identities so that users can actually keep managing their data and keep managing their keys without having to be scared about losing access to whatever is shared for them. And this is where we invented CALYPSO. CALYPSO takes any kind of blockchain, whether that's Bitcoin or some permission PBFT deployment, and deploys along it a second secret management authority, as we call it, which enables confidentiality. The architecture is very simple. We have writers and readers. Writers place encryptions on chain through write transactions, and reader retrieve the secrets through read transactions. The job of the blockchain, as before, is to have integrity and availability, and it also enforces access control. And the job of the extra side chain, the secret management authority, is to manage and deliver the secrets. I'm not going to go into detail of how the protocol works. The basic idea is using different kinds of secret sharing techniques and combining them with some other cryptographic protocols. But you can see in the paper two different protocols. One is called one-time secrets, and it's suited for permissionless deployment, which means that it does not need any bootstrapping. Wanda and Ron can simply agree on who they trust and run the secret the protocol. And it also has an incentive scheme to make sure that the trusted parties are actually staying alive to be rational. On the other hand, we have long-term secrets, which is more suited for a permission deployment. There, we need a bootstrapping step called distributed key generation, but the protocol is much more efficient because it does not blow the chain. It has constant ciphertext size, and it also handles churn. So the membership of the secret management authority can actually change without any problem. For further details and actually how we also achieve receiver anonymity in dynamic identities, you should look into the paper, or we can talk in a more detail. For the last 2 minutes of this talk, I'm going to discuss the deployment, implementation, and experimentation results. So with CALYPSO, we didn't just stay at the proof of concept stage. We instead work with partners to deploy it in the wild. Two deployments that we are currently working on is first on clearance enforcing document sharing. There, we have multiple mutually distrustful state actors, for example, national defense and security sector ministries, who want to share some very security critical document with each other in order to collaborate, but they want to enforce forensics. We want to really know who accessed the data for which reason and when. And we don't have any trusted third party to actually be the access control master. Secondly, we worked with hospitals to enable patient-centric medical data sharing and enable more fine-grained data sharing and patients to have control over who accesses their data, and also remove some of the stress and cost from hospitals who now no longer have to be the data carriers, because users are the ones that are giving consent on who accesses them. So for the implementation and evaluation, we implemented everything. We ran in a large-scale testbed, emulating the real network. And as you can see mostly in the paper, we pay not a very significant cost other than the distributed key generation, which is run once per epoch. The rest of the steps take 2 to 15 seconds, depending on the decentralization that we want. We also run with the document sharing application and compare it to centralized and semi-centralized solutions. And you can see that the overhead is not as significant for the semi-centralized to CALYPSO. Of course, the centralized is much faster, but what can we do? This is a system that has different trust assumptions. Finally, we also implement the decentralized lottery and show that with CALYPSO, we can do it much faster, especially as the number of users increases, because we no longer have to pay a logarithmic number of rounds. So this is CALYPSO. It enables fully decentralized auditable data sharing, and I'm open